morning to all of you. See, I will be starting with the aeroelasticity. See, before going to this turbomachinery aeroelasticity, you should learn aeroelasticity in a simpler form, because fixed wing aeroelasticity is relatively easy to understand, and then from there you can slowly go to unsteady aerodynamics. I will be talking of very simple, taking a simple model aeroelasticity. See, aeroelasticity is when we are doing the calculation of aerodynamics. Inherently, most of the time probably aerodynamics teachers does not tell about that we are taking a aerofoil which is flexible, but actually it is flexible. It means in a aerodynamics calculation it is inherently considered that the this aerofoil section is infinitely rigid, but practically it is not. It is having some flexibility. So, it will affect the structural performance when air is considered in the, or air flow is considered on the aircraft. I will be starting with the fixed wing aircraft and a simple aerofoil which is thin aerofoil. Usually we consider in the aerodynamic sense, we consider as a flat plate aerodynamics. Structurally it will be 2-dimensional or 3-dimensional, but aerodynamically it is a flat panel. Okay. I will start with the introduction of aeroelasticity, that is the topic whatever I have chosen. In this, basically in aeroelasticity we have two aspects, one is on the static sense, another in the dynamic sense. But truly speaking, static sense does not exist at all. But when we are saying that the aerodynamic load is not varying over a time, then I can consider a equivalent static condition. See, suppose when aircraft is flying in a air, means at some altitude, let us say 8 kilometer or 10 kilometer altitude, and it is going straight level flight, and let us say there is no disturbance. So, we can consider that it is a equivalent static problem, because aerodynamic load is not changing over the time. But suppose that when aircraft is flying, it is subjected to a sudden disturbance, a turbulence, then we cannot deal the problem with a static analysis, we have to go for dynamic analysis. In structural dynamics we have to consider, at the same time we have to consider the unsteady aerodynamic concept. Means see, when structure is oscillating, then the aerodynamics whatever we calculate, basically that is a steady aerodynamics, that no longer exists. So, it will be under dynamic condition, it will be unsteady aerodynamic load. Let us start with the definition aeroelasticity. This is basically mutual interaction between aerodynamics and elastic forces when it is in static sense, but in general when broadly we say aeroelasticity is the study of the interaction between inertia force, structural force and aerodynamic force on aircraft. I have considered as aircraft, but it may be on building surface, building also, surface vehicle also, means 4-wheeler or automobile sector also. There are some structures which may be subjected to aeroelastic effect. It will be there, but we may ignore, because it may not be that high, that is why we may ignore. Let us consider this we call as the aeroelastic triangle. So, we have aerodynamic load, elastic load, and then we have this inertia load. When these forces are acting, we have different definition. It is not always aeroelasticity. I will just go to that. First, I will consider that when elasticity and inertia is interacting each other, that we call as the structural vibration. And then we can have when we have these three together, aerodynamics and the inertia, means considering aircraft as a lumped mass which is having 6 degrees of freedom, and then the associated aerodynamics which is acting on the whole surface, 3D surface. If we are considering these two aspects only, finally taking the load, aerodynamic load to the aircraft CG, which is considered as a lumped mass, and it is having 6 degrees of freedom. What are those 6 degrees of freedom? 3 translations and 3 rotation motion. Then whatever we do the study, that we call as a flight mechanics. Then we have another one, static aeroelasticity, when I am considering only the aerodynamic load and the elastic load. In that case, only aerodynamics and elastic load is there. We are considering as a static aeroelasticity. In the static aeroelasticity, we have different things actually. See, when aircraft is flying in static aeroelasticity, there will be a load acting on the structure, and we have to find out that we call as the maneuvering load. It may be 1G level flight, 2G level flight, or depending on what type of aircraft I am designing, the trimming condition will change. I am sure you have heard about trimming condition. Aircraft is trimmed, means at a certain condition, means the elevator deflection, angle of attack, and maybe some other control surface deflected in such a way that it will be in equilibrium. All the forces acting in a particular direction will be 0, all the moments acting in the particular axis will be 0. Then only we will call that call as the trimmed condition. We can have different trimmed condition, means we can have 1G level flight, means aircraft is going with a 1G acceleration which is acting upward acceleration, but inertia force is acting downward. So, means acceleration, if acceleration is upward, I am sure you have heard about the D'Alembert's principle. No? When the acceleration is upward, the inertia force which will be acting on the aircraft will be opposite to that. Sorry, I think in this case acceleration will be acting downward, and then inertia force will be acting upward. Okay, so sorry, not inertia force will be acting downward due to the gravity of the aircraft, and the lift force whatever acts on the wing, that will be acting downward, upward. So, this will be balanced. Usually what we do, we balance this vertical motion and we balance the pitching rotation. The whatever lift moment is developed due to this means eccentricity of the aerodynamic center, there will be a moment about the elastic axis or moment about the CG point, and we have to deflect the control surface in such a way that that moment will be balanced. Then we are calling as the these two basically for symmetric maneuver, these two has to be balanced. The vertical all the forces in vertical direction has to be balanced, all the moments acting about the y axis should be balanced. Then it is means symmetrically trimmed and aircraft can move forward. I am not means equating the forces in that direction. Means if I equate in the means forward direction, then there will be forces, your thrust force is acting there, and the drag force, and then forward force. These forces has to be balanced, then only it can have a constant velocity or constant acceleration forward motion. Aircraft can go, those are the maneuver condition we can have, because for a transport aircraft usually we do not need many different type of maneuvers. It means simple, it takes off from, it starts from the tarmac, goes to the means runway, starting of the runway, it picks up the velocity and it attains a velocity when the lift and the inertia force is balanced, then only it can take off. And usually it takes off, goes to a certain height and then goes in a level flight. Again when the airport has come, it will start descending and landing. This is the usual maneuver for a typically transport aircraft, but in between suppose there is some disturbance. If aircraft is designed for that disturbance, usually aircraft is flown by the means pilot is there, but pilot will take the decision once ground control system how they are means directing them, whether they will follow the same path, defined path, or they have to deviate from the path. So, I am saying in that sense your transport aircraft maneuver conditions are very simplified. But if you go to fighter aircraft, there are several type of maneuvers it has to perform, and normally the load levels will be very high. It can go up to 8G. Means typically the light combat aircraft scenario, we have maximum 8G level flight, 8G maneuver, and then there will be some side slip or rolling. All these combination we can have a maneuvering condition. Means maneuvering is not a only one type of trimming. There are several trimming. Trimming in the sense means putting the forces into the equilibrium, because the aircraft is in slippery condition. The forces whatever is acting in the clockwise direction and anti-clockwise direction has to be balanced. That is the trimming condition, and then we can combine 2-3 different trimming condition can have a maneuvering conditions. Okay. So, this is the static aeroelasticity, and static aeroelasticity is very important from our design point of view. In the initial stage of aircraft design, static aeroelasticity is main driving force. And then we have another important thing is that control reversal, because for different maneuvers or the trimming condition, the control surface has to be deflected. So, the control surface we can have a deflection up to certain velocity. This deflection is stable. We can means the aircraft may achieve a velocity which is such that the lift or the moment, counteracting moment whatever is acting on the control surface, and the control surface is mounted on a this mechanism, control mechanism. So, that is having a particular stiffness. When this aerodynamic moment and the control stiffness is balanced, then we call as the situation control reversal. That control means aircraft means pilot is trying to change the means angle of means control surface deflection, but he is not able to, because it is not effective. The both forces are cancelled each other. Then we can have another means that is the load redistribution, because we can initially consider means in the beginning of the aircraft analysis, we usually consider the aircraft this aerodynamic load will be rigid load, and then we proceed with some design, because design is not a one step means for only forward, it is a iterative solution. So, once we go for that, there will be a lift distribution, but when I am considering the flexibility of the structure, it will be load will be redistributed. So, that is the actual load whatever is acting on the structure, that is important for our calculation. Then we have when these three forces are acting together, the aerodynamic force, elastic force and inertia force together, then we can have the dynamic aeroelasticity. We can have typical means phenomenon of dynamic aeroelasticity. One is the flutter, that is the important parameter. It has to be designed in such a way that in the designed envelope, means designed envelope in the sense depending on what altitude maximum, what is the velocity it can achieve, that envelope we are calling as the flight envelope or designed envelope. The aircraft design has to be such that flutter should not happen within that envelope. There should be usually it says that mil spec says that 15% margin should be there, but another riding on that is there. Any mode there should be 3% damping available. So, both together once we satisfy, then we can say this is okay, means aircraft can fly. but that is possible when that measurement of damping possible when you are in the flight. Before flight, in the design stage, we do not have any estimation of damping, because damping we cannot make a mathematical model, it is very difficult. We can make a mathematical model for elasticity, we can make mathematical model for mass, but we cannot make any mathematical model for damping. What we can do actually, we can assume some damping and proceed with that. See, if whether I am taking any damping or not, if I ignore the damping, that is basically I am designing a conservative design. Damping is there, then the margin will be more. So, that way, and another important part is the buffet. Buffet means if you have a tail wing, typically tail wing construction in the aircraft, when air is passing through the main wing, it will be hitting, because it will be disturbed, there will be a vortex generated and that will be hitting the tail wing, and that in a particular let us say angle of attack, that may happen, and that situation we are calling, means that type of analysis we are defining by a term called buffet. That has to be also in some particular type of aircraft, it has to be designed in that sense, it will not have any problem. Another important part is the gust response. See, this gust response, gust is not a problem for fighter aircraft, because aircraft is designed for a very high maneuvering load, whereas the gust, whatever it will means, when there is a disturbance, obviously pilot will not go for a high maneuvering condition, they will be going for the simple 1G level flight. So, 1G level flight plus gust load, whichever load combination is coming, that is much below the 8G level flight. That is why usually it is not very critical for the fighter aircraft, but it is very critical for transport aircraft. Transport aircraft, because it can fly maximum up to 1.5G or 2G, not more than that, and if there is a disturbance, means gust, usually size of the transport aircraft will be very big, and that is why the effect of gust load will be more in that transport aircraft. And we have to make a means do the analysis, design it and clear from the flutter point of view, gust point of view, means in addition to static load, maneuvering load, you will have a this gust load. See, usually it is done this way. Let us say aircraft is flying at 1G level flight, we will have a particular load case, a deformation case, and then we will do separately the gust load analysis, means considering the modal concept. See, static analysis I can do in a physical model, but dynamic analysis I cannot do physical model, because it will be very difficult and expensive also. So, we do always in the modal domain. So, it will be done in modal domain separately, gust analysis, and we will consider that it is a linear elastic analysis. So, we will superpose these two displacements together and then monitor the stress values at different parts of the aircraft, whether it is within allowable limit or not. Okay. This we are calling as the aeroelastic triangle, sometimes we call as the Kohler's triangle. There is another vertex when control force is also coming into picture. So, all these three forces, aerodynamic force, elastic force, inertia force and the control force, tetrahedron, then we call as the aeroservoelastic analysis. That will be, that is actually practical. Up to this, it is only considering without considering the control in the loop, but control has to be considered in the loop, because that is the pilot has to do that maneuvering conditions, and there will be interaction between structural dynamics and the control dynamics. So, that is also important part, but so far means in this discussion I have not considered that. So, let us see why it is important, the aeroelastic analysis. The interaction between three forces can cause several undesirable phenomena, that whatever I have discussed, divergence. So, you have to find out the divergence speed, that divergence speed should be beyond our flight envelope. And then another is the flutter. Flutter is the dynamic instability. See, in the divergence we call as the static instability. Means how we are interpreting this, physically how I can interpret this. Divergence, see, structure is having some stiffness. Usually when I am talking of the flutter, divergence, I am talking of the torsional stiffness. The aircraft is having some particular torsional stiffness, and that is basically restoring force, and aerodynamic force is acting to deflect that. But suppose aircraft is flying in a particular speed, where whatever aerodynamic moment is generated, that is cancelling the structural stiffness, then we can think of that a structure without any restoring force or spring stiffness. So, that now under that condition, suppose I give a perturbation, a small deflection, that will go to a very means mathematically it will go to infinite deflection, but practically it does not happen, because whatever we do the analysis based on the linear analysis, moment it goes to high deformation, it will nonlinearity come into picture. Obviously, it will not have infinite deformation, but definitely when it enters into the divergence, deflection will be very high. If that deflection induces strain, deflection will induce strain, strain will induce stress, because due to the elasticity. Deflection and the strain, these are physical parameters. Stress is not a physical parameter, it is a mathematical parameter. So, that stress whatever is developed, that has to be within the allowable limit, then only we can say the aircraft is free to fly. That is why I am saying, but usually divergence speed, the design is such that divergence speed will be far beyond the flight envelope. So, that way it is not that critical, but flutter is very critical. Flutter, it may come within the design envelope. I will just give you a simple example. When this our LCA now named as Tejas, it was designed in started the design 1984. That time whatever missile configuration, because fighter aircraft is designed to carry certain means activities, no, it has to carry bomb, it has to carry missile, it has to carry drop tanks, several things are there. There are usually in the below the wing it will have 3 stations, and below fuselage there will be 1 more station, 7 stations are there. So, when it has been conceptually designed in 1984, that time the missile configuration whatever was available in the market, that we call as the R60. This is what we procure from outside Israel. Some configuration was there. That configuration was lighter, and from elastic means inertia point of view also it was not that critical. But when it came to almost to the final stage of the design in 2001, that time the new configuration of missile has come. That one was R73. The configuration is slightly different, CG position is different, longer, and inertial position is different also. Inertial characteristics are different. When that same missile is put on the earlier design, it has been found that the flutter is happening within the design envelope. So, there are 2 options, either you restrict your envelope, obviously Air Force will not allow to do that. You have to, because they will say then I do not need this aircraft. If it is not able to meet the design envelope or our requirement, then what is the use of that aircraft? But as there was a possibility of redesign, so next option was to redesign the aircraft. As it was made of, the aircraft wing was made of the composite, that is why it was possible to make the change the design. So, what they tried initially, stiffening the wing portion where it has been mounted, the local stiffening, and then finally we could solve that problem. But we do not know, after maybe another 15 years another new configuration will come. Same thing may be happening in our this Mirage 2000. we have procured long back already 15 years. Usually life is 15 years for each aircraft. We have crossed all those, and now new configuration has come. They have tested it. Obviously, without test, pilot will not fly. Test and prove that it is means there is no problem, then only it will fly. Same thing may happen in the LCA case also, this Tejas case also, but for the timing it has been cleared. Means whatever configuration, bomb, your missile and other means attachments are there, that is satisfying the criteria. Then we have one more limit cycle oscillation. This is a nonlinear aeroelastic phenomenon. This typically it may happen when there is a free play nonlinearity. There is another option, means when missile is fitted to the aircraft wing, there are some means fitting arrangement we call as the pylon. It will be fitted with the wing, and then that is called pylon. That is an interface between the missile and the structure. And missile and the structure this pylon and the missile, there may be some free play. So when it is flying, there may have some this nonlinear aeroelastic problem, what we call as the limit cycle oscillation. This is similar type of problems are there in the control also. Flight control also, flight mechanics also. Then we have certain other things, vortex shedding, buffet, galloping, those are all unsteady aerodynamic load phenomenon. Then okay, see whatever we do the test analysis, analysis is not sufficient. Our certifying agency, I am sure you are aware of that, we have a certifying agency. So, the certifying agency will not allow as long as you are not proving in the experiment or practically. So, whatever we do the analysis, we have to show in a simplest, maybe full model or maybe in a scaled model. Usually what they do in a wind tunnel, they do the scaled model means wind tunnel analysis or experiment, and then prove that it is free from the this static divergence or other things. Here I have shown here a means in a wind tunnel a flat plate is mounted. If you look at here, let me just if you look at here this position, sorry. This is not there. This mouse is sorry. If you look at this portion, this is a flat plate. This is a flat plate mounted on a test section of the wind tunnel, and then they increase the speed. Today I will also show you in our wind tunnel. We have a Flutter model that also can be we can perform with that model also the divergence experiment, and then another model they have shown here that is also flat panel. Then flutter, see usually in the ground we cannot do any flutter, but in the wind tunnel whole aircraft may not be possible. Sometimes if we have bigger means test section, probably full aircraft maybe we can take scaled full model, but sometimes we demonstrate that by taking a wing only, wing fixed at the wall, cantilever wing kind of thing, scaled wing model, and then do the test. There this type of limit cycle oscillation also we can show if we put some free play here in the connecting mechanism, then limit cycle oscillation can be demonstrated there also. Then we can have another okay, just I am just telling you what is this flutter. Flutter means it will be a situation when there is the overall damping in a system is 0. Structure will be having a damping that usually we consider as the positive damping, means if damping is there, that will dissipate the energy and amplitude of oscillation will come down. But in the flutter situation, the overall damping in the system will be almost 0. So, we cannot means if we fly beyond that, what will happen? It will start oscillating like this. This is some simulation kind of thing. That is why whatever we are finding, that it is not failing, but it is oscillating. But we can have another type of simulation with a full aircraft. Full aircraft, this is simulated in some software, most probably it is in MSc Nastran. This right now whatever I know, MSc Nastran is having the full aeroelastic model. This ANSYS, they are saying that it is there, but still they are not able to demonstrate in a full aircraft model. Then if there is a failure, what will happen? Suppose there is a flutter in a control surface or tail wing. What will happen? Tail wing may means shear off from the structure. So, what will happen? The pilot will not have control to control the aircraft. So, one option, if he can means recover the aircraft, that is well and good. Otherwise, he has to usually for most of the aircraft, fighter aircraft, this is some typical fighter aircraft. Most of the fighter aircraft will have a ejection button. So, if he is not able to recover the aircraft, at least he can save his life. So, he can press the eject button and then pilot will be ejected from the aircraft. Aircraft may fail, but pilot life will be saved. This is another, means this is the physically whatever it has been observed. Probably you have heard about Tacoma narrow bridge. They have means constructed a bridge keeping two supports almost towards the bank of the river, and there was a long span, and that width of the that bridge was not that high. So, what they observed means width less means, and also they have designed maybe from the structural point of view. They have not considered the flutter condition. So, they have not given enough torsional stiffness to the bridge construction, this particular bridge construction. So, what happened when this bridge was opened, there was a wind of not very high, something around 40 miles per hour, that one was the wind. Then they started observing that it is started oscillating like this. That also you can means whatever you are seeing from here. Sorry. In this, see, it started oscillating like this. Probably somebody was there, because this is the opening day. Some cameraman was there, that is why he could capture the video. And then finally what happened? Within half an hour of the opening of that bridge, it collapsed. Maybe some problem is there with this, and it is not means then it failed. But that is not the first time it is observed. This if I show you, the flutter or aeroelastic phenomenon has happened since First World War, but that time it was not clear why these aircraft has been failed. Slowly they started learning what is the issues. Then later the design was taken care of those aspects. I do not know, this also there is another, let me just see whether it can play or not. No, I think it is not playing. No, it needs some particular player. Okay. So, so how to avoid these things means basically we have to consider the aeroelastic aspect during the design phase, and obviously we have to do some wind tunnel testing, because analysis we have a lot of assumptions, and that may not be accurate enough, but analysis is important. analysis. Without analysis we cannot proceed for the design. Then once aircraft is ready, we need to do ground vibration test, then flight flutter test. That is the actual when aircraft is means cleared for flight, there you have to demonstrate that damping means pilot will be giving certain pulse and measuring the responses, and then the ground engineer will do the calculation, say that the damping for each different modes are above 3% damping. So, it can further proceed for the next test points. There are some wind tunnel testing and ground vibration testing, engine ground vibration testing, where aircraft engine will be mounted as a free structure, and then at different places through the shaker it will be excited, and there will be some accelerometer placed at different places. Response will be collected, and through the software it will be extracted the frequencies, mode shape and the damping associated to those modes. And this is another ground vibration test under vertical means horizontal what do we call as the ground vibration testing. Horizontal ground vibration testing is the space shuttle, which is mounted in this horizontal means usually we put it in the horizontal, it is in the vertical phase. Though it is saying horizontal GVT, means GVT the excitation is given in the horizontal direction to find out the response of the system. Then the flight flutter test. This is typically the flight flutter test when aircraft is flying. Aircraft is flying through the control mechanism, there will be a certain pulse generated to give it to the control surface, which will be exciting the whole aircraft. It may be symmetric pulse or it may be antisymmetric pulse, and then usually the first aircraft of the in the design phase, first aircraft which is produced, that is usually it is instrumented, not only one actually. For a fighter aircraft usually there are 7 aircrafts in the series, and those aircrafts most of all 7 aircrafts are instrumented. During the flight all data will be monitored. So, pilot will be giving a certain pulse, response will be monitored through the telemetry to the ground station. The ground engineer will do the analysis and say whether damping is within, that is whatever the plot is here, the damping for a particular mode, it has been monitored, it is found that it is more than 3%, means 0.03, more than 0.03. Then, and this is the frequency, then it is free at that point. So, it can go to, means it is clear at that point, because in the flight envelope there are several points, test points. So, those test points has to be performed and then get a clearance, then he can go to the next point of test. So, basically in this course whatever I will be talking of briefly about the static aeroelasticity and the dynamic aeroelasticity. Just this semester I have taught this subject, it is not for 2 hours course, it is actually 40 hours course, but briefly I will give you the idea how we can proceed about the, I think certain parts I can means there are certain historical aspects that is there already, you can go through it. Let me come to the static linear aeroelastic analysis. What I am considering here, a thin aerofoil which is, see, if there is a aerofoil, we can consider that it is means aircraft wing is connected to the fuselage. Fuselage is acting like a support. So, for a wing it is a cantilever wing, and this cantilever wing will have bending stiffness, bending in this direction, and then torsional stiffness. Torsional means about rotation about the y axis. Usually aircraft axis is like this, tip of the aircraft is the origin, and then towards rear side of the fuselage, that is x axis, this side it is y axis, and then it is z axis. That is the means the stiffness about y axis, what we call as the torsional stiffness. So, if we look at the equilibrium equation, when lift is acting on the structure, we will have two equilibrium equations. One is the torsional equilibrium equation, another is the bending equilibrium equation. But torsional equilibrium equation is mainly responsible for the flutter, divergence or the static aeroelasticity, whereas bending mode is not responsible for flutter. That is for different configuration, it is depending on position and orientation of the wing, bending may come. So, that is why usually what we do actually, the torsional equation which is free from bending response, means is uncoupled from the bending. So, we considered a aerofoil section with only single degree of freedom, which single degree of freedom means rotation about y axis, the pitch angle. So, when aircraft is flying, there will be angle of attack. With that angle of attack, there will be a lift generated. Due to that lift, whatever lift generated, it will try to rotate the aircraft wing. So, there will be a rigid rigid angle of attack. Due to the load, whatever lift load is acting, that will give a additional deformation, that we are calling as the flexible angle of attack. So, alpha r if I consider as the rigid angle of attack, then theta I will be considering as the flexible angle of attack. So, these are typically we consider that. C, you will find that in several calculation we consider B. C is the chord length, B is the semi chord length, C is nothing but twice B, because certain parameters are defined with respect to the semi chord. Because semi chord, why we consider semi chord? When it is in dynamic condition, we can imagine that there is a air column which is equal to the radius of the this half semi chord, and that fluid is also acting on this wing, means affecting the wing with some inertial load. That is why sometimes we consider half semi chord, not the full chord length. That is why I have written here C is equal to twice B. We have a elastic axis about which it rotates, that I am calling as the elastic axis, and with the elastic axis I have just mounted a spring. That spring constant is k theta, and there is a aerodynamic center. When we are considering steady aerodynamic load, that aerodynamic load acts from a point, quarter chord point, that we are calling as the aerodynamic center. Then there is a eccentricity from aerodynamic center to the elastic axis, we are defining by E into C. E is the eccentricity multiplied by C. So, if I proceed with that, first I can calculate the lift force. How I can calculate the lift force? The dynamic pressure, this is first part is the dynamic pressure into area multiplied by CL, lift coefficient. That total will be giving us the lift force. This is the lumped lift force, but actually our aircraft wing is not a it will not be considered as a means this in this basically whatever small aerofoil I have considered, considering that the wing span is infinitely long, and that is why I am idealizing the whole wing as a with a simple aerofoil section and taking a spring constant. This is the simplest model, but with that also, yeah.
So, theta is like we are taking average at that particular spring where it is attached, or it is actually varying, or how it is varying, linearly, or it is average?
No, it is constant.
It is constant. We are taking average of.
It is constant about the elastic axis. The angle of attack whatever we have considered, and that is about the elastic axis. Okay. And in addition to that, whatever angle is there, that will be considering as about, means we are considering that along chord length the bending stiffness is infinitely rigid, if you look at that way. Am I clear? Means we have bending stiffness along the span, there is a bending stiffness along the chord also, inherently I am considering that the bending stiffness along the chord is infinitely high, and so whatever additional rotational angle will be there, that is constant for entire chord length. Wherever you measure, it will be same, means it is a idealistic design, because when we start the design, no, we have to start with a very simple thing. We cannot go to a complex structure as long as you do not have that, because when we start the aircraft any design, we start with a, means for a aircraft design we start with two aspects, means what type of engine I will be using, what type of maneuvering condition I need. So, if I need this much maneuvering condition, how much lift I have to generate it, what should be the lift, means aerofoil configuration, and how much is the area. Then it comes to the structural design. Initially it is flight control, aerodynamics and propulsion. These three will be playing a role in the initial design. Then slowly we will modify, we will come to the structural design. Finally, if I define this is my planform area, then we go for internal structural design. So, if I look at here this lift force, then if I define this S, whatever C I have considered, I am considering perpendicular to that is unit. So, cross sectional area will be C into 1, and this will be CL means lift coefficient is nothing but CL alpha into alpha. CL alpha is the lift curve slope into alpha is the angle of attack. In this angle of attack, I am saying there is a rigid angle of attack plus theta. That is what finally I have step by step I have shown it how it is coming, but this alpha I am considering as alpha r plus theta. Alpha r is coming from the initial angle of attack, theta is coming due to the elasticity of the wing. And then similarly I can calculate the moment also. From moment also I will, because this moment whatever I am considering here, this moment is due to the camber length. Without any angle of attack, there may be a lift, depending on if it is a symmetric aerofoil, there will not be any moment. But if it is an unsymmetric aerofoil or cambered aerofoil, then there will be a moment, zero angle of attack, there will be a moment. That I am considering as MA0. Then we can go to finally the total aerodynamic moment calculation, that MA I will be calculating here taking alpha r plus theta, and then we have Q, Q is the angle of attack, dynamic pressure, E into C square means EC is the distance between the elastic axis and the aerodynamic center. The whatever lift force is acting multiplied by E into C. So, that finally it is coming as Q E C square CL alpha alpha r plus theta. Alpha r prime I have given if there is a this zero angle of attack moment is there, then I am taking that. So, finally, we can for simplicity alpha r can be considered as alpha r prime can be considered as alpha r. And similarly, from the structural point of view, lift is trying to rotate in this direction, the structural stiffness will be trying to restore it back. So, the aerodynamic structural moment whatever will be there, that is k theta into theta, which will be acting opposite to that. See, alpha r is for the rigid angle of attack, means for the whole aircraft there is a angle of attack, but due to the flexibility of the structure, whatever additional moment is coming, that will be restoring by that will be restored by the this elastic stiffness. So, this under equilibrium condition I can say that total aerodynamic moment should be equated to elastic torsional moment. So, if I take this equation, finally, I can get the value of theta, solve for it, and I can calculate the theta. Theta is coming from here, this equation, simplifying from the means the equilibrium equation, and I can write this theta. So, there will be a equilibrium alpha equilibrium, that I am saying means what for a particular velocity alpha r plus theta, whatever is coming, that is the alpha equilibrium, and I can calculate the theta with respect to the non-dimensional parameter. There I will be getting a condition, means this theta can be can become infinite when the denominator of this equation or this equation will become 0. Then theta will be infinite, mathematically theta will be infinite, and if I find out what is that value of q, that I consider as the QD, that is the divergence dynamic pressure. That is what I am writing here. QD is nothing but k theta divided by E c square into A. A is nothing but CL alpha, sometimes we write as the A, short form, angle of means lift curve slope. So, from here I can calculate the theoretically I can calculate what will be the divergence speed. Once I know the divergence dynamic pressure, half rho v square. So, from that I can calculate V. If it is flying at, let us say, sea level altitude, we have some certain density of the air. If it is flying at 1 kilometer, 2 kilometer or 10 kilometer, then the density of the air is different. Accordingly, divergence speed will be different. Divergence speed for all altitude, it is not same, but divergence dynamic pressure is same. So, velocity will be different at different altitude, because stiffness does not change, structural stiffness is fixed, only the aerodynamic moments changes with the altitude. So, that way I can find out what will be the this divergence speed or divergence dynamic pressure. Experimentally, we can do the experiment to find out how much means if I look at back, just go back here. If I express this theta, when I am saying QD as the dynamic pressure, I am rewriting this equation in a non-dimensional form. Theta is expressed q bar alpha r divided by 1 minus q bar, and I am writing this equation in this form, theta by q. Finally, after manipulation I am writing this equation, theta by q is equal to theta by q d plus alpha r plus divided by q d. Alpha r is a constant. So, I can equate this means relation as a straight line equation, y equal to mx plus c, where y is nothing but theta by q and x axis is theta. If I can measure for different dynamic pressure for different speed of the speed in the wind tunnel, I can calculate q, and also I can measure what is the additional deformation. That if I plot there, this equation will be a straight line equation, and I can get the divergence dynamic pressure from the this slope of the equation, y equal to mx plus c. That m I can find out basically 1 by qd. 1 by qd is my slope. From there I can find out experimentally I can find out what will be the divergence dynamic pressure. Okay. I think we can stop here. Then I will go to, I think let it be here up to static, then we will start. I will just briefly give you idea about the dynamics. There are several other slides also, but if I want to cover all these, then I may not be able to cover by 12 o'clock. So, we will have some break, or I will continue. You need some break? After that, then if you need break, then I will after break I will start with the dynamic aeroelasticity. Just to give you introduction. Up to static aeroelasticity, do you have any? This is k theta. K theta is a structural stiffness, and q e c square a, this is also stiffness, but it means get a flat panel. The fan blades or the blades in stator, rotor, those things are complex geometry, and whatever I am just talking of the static aeroelasticity, that may not exist in the rotating device. That is why exactly we cannot get a phenomenon in the aeroelastic static aeroelastic effect in a rotating system. But if I consider means what will be the structural point of view, what is the difference? Means suppose the geometry is known to me, we can calculate, and material is known to us, then we can calculate the stiffness of the structure. But in addition to the stiffness of the structure, that is the inherent stiffness of the structure, and in addition to the stiffness of the structure, when a rotating blade is there, there will be a centrifugal force acting down means outward. So, it will be applying a force like a tensile force on the structure. So, that will induce some stress and strain, and if it is under a thermal environment, so that also will be inducing some strain, thermal strain, and thermal strain will be finally act as a thermal stress. So, in addition to structural stiffness, what I can take basically, we have to consider these two stresses as a initial, means that is always acting. We can take as a initial stresses. So, these initial stresses will be inducing some initial stiffness. That what in structural point of view, what we call as the geometric stiffness, or sometimes we call as the initial stress stiffness. Means if it is tensile stress, so stiffness will be increased. If it is compressive stress somewhere, then the overall stiffness of the structure will be reduced. From the structural point of view, that is the difference, but aerodynamically there are a lot of differences there. So, that whatever we have considered simple taking a means lift curve slope, that may not be directly applicable in the rotating device with a blade, complex geometry blade. The geometry is very important in the aerodynamic calculation. Let us start with the aerodynamics, means dynamic aeroelasticity, then I will see how we can correlate. Okay. See here I have considered in the static aeroelasticity, what I have mentioned, that I have mentioned that only I am considering a torsional stiffness, means torsional equilibrium equation. Torsional equilibrium equation is not coupled with the bending equilibrium equation, whereas bending equilibrium equation is coupled with the torsional means equilibrium equation. As I am in the static analysis, I am solving only the torsional problem, I do not need the bending equation to be considered. But in dynamic situation, I need to consider both static means bending deformation, that whatever we are calling as a pitch plunge, means in this direction plunge mode, and the rotational mode, pitch mode. Pitch is the rotational mode about y axis, and plunge is the vertical deformation. That is whatever we are finding here. This kh I am considering as the bending stiffness, and here also I have used k alpha, means torsional stiffness, that is equivalent in the static analysis we have used k theta, because some books they are conventionally following k alpha as the in the dynamic situation, k alpha is the stiffness, torsional stiffness, and k h is the bending stiffness. H means in the plunge degree of freedom whatever we define by h, that is why I am using as k h is the bending stiffness, k alpha as the torsional stiffness. And there are different points. You see, earlier case we have considered only aerodynamic center and the elastic center, but in dynamic situation I have to consider CG position also, because CG position also plays a role in the dynamic analysis. That is why I have to consider the CG position also. If you look at here, from the tip we have xf, that is the distance of elastic axis from the tip of the wing or aerofoil section. Then we have xc, that is the CG position from the leading edge of the aircraft or aerofoil section. Then we can go to the first, let us see structural model. There are two aspects to each aeroelastic models. One is the structural model and another is the aerodynamic model. Means structural model, whatever you have learned the structural theories, that will be applicable here. There is no difference as such other than whatever you have learned, but that is what I am saying. In addition to structural stiffness calculation, we have to consider these two different forces, thermal forces and the centrifugal forces, to get total stiffness of the structure, that we call as the effective total stiffness of the structure, which is playing in the aeroelastic model. In some cases, a control model is also added to represent the effect of actuators and other control elements. In the example, I have taken a aerofoil section with control surface also. I have given some figures, not the mathematical details. Mathematical details are there in the books. I think I have not given any reference here. No, I will give you tomorrow. I will give you by mail. Probably I can circulate you which are the reference book you can follow for aeroelasticity analysis. Those are the standard books available only. Only 4-5 books are available. Those are the books you have to consider. And in the development of the structural model, what we have considered here, we have applied a energy method. Basically, structural model in the sense, I have the structural element or geometry known to me, and the material properties is known to me, density of the material is known to me, then I can make a structural model. What I am saying that first, in terms of the energy conservation system, energy conservation, from the energy conservation model, what we know that energy cannot be created, energy cannot be destroyed. This is just it can change from one form to the other form. So, that is why first I am what I am calculating here dt, that is basically the dynamic kinetic energy. So, half dm, that I am considering a small mass over this aerofoil section, and mass of that small portion is nothing but dm, and then I am considering h dot, means the half mv square. So, h dot plus x minus xf into alpha dot, because earlier case it was only rotating, but in this case it is rotating plus deforming also, bending deformation is also there. So, if I consider that the deformation of the alpha, means effect of alpha is on the overall deformation of the h, that is coming h plus x minus xf into alpha dot, that is the total deformation at the this actually at the center of x minus xf. Okay. Actually, it is difference between the elastic axis and the inertia axis. X, it has not been defined here. X is basically the position of the CG. Another important part is that for a aircraft, CG is not a fixed point, it varies, because how much fuel you are using, it based on that it may vary, whereas the elastic position is fixed. So, this h dot plus x minus means theta into x, that is the means if I plot this way, means take a angle, if I take a angle, just 1 minute. If I take a angle here, see this angle, let us say this is theta or alpha, I am taking here alpha, the deformation, this deformation due to this alpha will be, let us say this distance, whatever I have defined as x minus xf. This is basically your elastic position, this is your center of gravity position. So, in addition to h we have deformation this x minus xf into alpha, basically tan alpha, but tan alpha is small. So, we can approximate tan alpha is nothing but alpha. So, this equation is whatever we are getting at the center of the center of gravity h dot plus x minus xf alpha dot whole square is the kinetic energy, whatever finally it is coming here. Okay, I think you can proceed. So, so kinetic energy we can have some more, that is the in a simple form I have expressed here. So, this kinetic energy finally if I take the mass, this is mass in the linear mass. So, means mass is also having relation with the angle of means degrees of freedom, mass with the h, that is the total mass, but rotational mass will be slightly different, that will be calling as the mass moment of inertia. That I am that's why I am writing here half m h square h dot square, h dot means whatever I have considered earlier at the CG, then s h dot alpha dot plus half I alpha alpha dot square. I alpha is the mass moment of inertia into alpha dot square. So, this s I think s is defined here c by 2, that is the mid chord minus xf, that is coming due to coupling is coming due to the eccentricity of the elastic axis position from the mid chord. And then finally, this I alpha also I can calculate, I alpha also I can calculate, that is 1/3 m c square minus 3 c x f plus 3 x f square, that is the mass moment of inertia. Mass is coming and the distance square is coming, mass into distance square, that is the mass moment of inertia. And similarly, I can calculate the potential energy. Potential energy for this heave motion or the plunge motion, half kh into h square, stiffness into means basically half into force into distance, whatever we calculate in our elasticity theory, half sigma into epsilon or half sigma force into displacement. Here also same thing, kh into h, that is the force, bending force into h, that finally it is coming kh multiplied by h square, that is the bending displacement square, that is the potential energy. Similarly, potential energy due to the torsional motion, half k alpha into alpha square. Usually in the calculation we neglect the gravity load. Then what we can calculate now, the total energy for the system is kinetic energy plus potential energy. We can finally express okay, that is the total energy, but from the concept of conservation of energy, basically we are applying here the Lagrange equation, which says that if I take the derivative of the total energy with means first taking derivative with respect to the velocity and taking time derivative, then adding the potential energy, this is V is nothing but potential energy. Potential energy taking derivative with respect to q, the displacement, okay, that should be equal to 0. This is the Lagrange equation. Lagrange equation says that if I take the derivative of the total kinetic energy, T is the kinetic energy taking derivative with respect to velocity and taking time derivative of that, plus dV by dq taking derivative of the potential energy with respect to the displacement, adding these two together should be equal to 0. See, in the static situation it is different. Static situation we will calculate total potential energy, and if I take derivative with respect to any degree of freedom, it should be 0, because energy is conserved. Similarly, the dynamic equation, in the dynamic equation I have to take a time derivative also, because kinetic energy depends on the time derivative. That is why we are taking time derivative of the derivation, which is in the kinetic energy, the degree of freedom is velocity. In the means potential energy, degree of freedom is nothing but q, displacement. That is why adding these two together, it will give us basically the equilibrium equation in the dynamic situation. And here the 2 degrees of freedom, whatever we have considered, q, I am saying the displacement vector, the 2 deflections. One is the h, the plunge motion, and the alpha is the rotational motion. These are the 2 degrees of freedom what we have considered here. So, finally, if I apply that equation, we will be getting a equilibrium equation like this: m s s I alpha, this is the mass matrix, into h double dot alpha double dot acceleration, then we have k h 0 0 k alpha. This is stiffness matrix, h into h and alpha. These are the 2 degrees of freedom. In general, suppose I am considering for a let us say blade structure, I have taken completely not only 2 degrees of freedom, I can take n number of degrees of freedom depending on how I am modeling it. If I am taking n number of degrees of freedom, then I can say that mass matrix, that is what I am writing here in a simplest form. Mass matrix capital M is the mass matrix into q double dot acceleration plus k is the stiffness matrix into q, right hand side I am writing as capital Q, means force whatever is acting on that. In this case, as we have not taken aerodynamic load, that is why I have written it 0, right hand side 0, but in our normal other cases there will be aerodynamic load, because we are talking of aeroelasticity, dynamic aeroelasticity. So, right hand side will be aerodynamic load. The first equation whatever we got, that will give us the modal analysis, the frequencies and the mode shape for a structure where there is no damping. That is why when there is no damping, whatever mode shapes means frequencies and mode shape we extract, we call as the normal mode analysis. Why it is normal mode? The damping actually changes the orientation of the, if we see the vectorial representation of the forces, how this inertia force, how this stiffness force, how this damping force is acting. If you look at that, you will have, let us say x axis is the stiffness matrix, stiffness force, then in this damping force will be acting perpendicular to that, because displacement and velocity there is a 90-degree phase difference, and displacement to acceleration there is a 180-degree phase difference. When there is no damping, if we express in a vectorial representation, we will find that these two means damping force is not there, these two forces align together, and we can normalize the system with respect to our modal vector. That is why we call as the normal mode analysis, but we can take damping also. Damping, if I take damping, then what will happen? My frequency, whatever frequencies I will be extracting, it is a complex number. Whatever mode shapes I will be extracting, those are also complex number. So, there we have to consider means eigenvalues, we have to take the real imaginary part for finding the damped natural frequency, and the modal vector I have to take the absolute value to find out the modal means modal vector, that is the actual value means amplitude. But problem is we need to consider the phase angle also, otherwise it will not say which angle it is, whether it is positive or it is negative, because amplitude always it is positive. So, phase angle if I am not considering, it will, you will not be getting how it is oriented. That is why, but usually we will be extracting complex means eigenvalues in the modal means Flutter analysis, but not normal mode analysis. But normal mode analysis I will explain to you why it is important, because when we are calculating the aerodynamic load, we need a deformed shape of the structure. Okay. Because unsteady aerodynamic load, when I am calculating, I am considering that it is vibrating in a particular mode. Either it is vibrating in a bending mode, or it is vibrating in a torsional mode, or it is vibrating in a combination of bending torsion mode. There are several modes. When I am talking of a complex geometry, it will not be the bending and torsion, whatever I am talking, it is for a simple configuration, it is fine. But when I am taking a complex geometry, these modes means defining the mode shape is very difficult. We cannot say it is the only bending or only torsion, it is a combination, always we will have combination. And what usually we do, we take some first few modes, those are the deformed shape to make the calculation of aerodynamics, and that way it will be coming as the modal aerodynamic load coming from the unsteady aerodynamics. See, okay, I will proceed, then I will show you another important part. So, aerodynamic model, see, for a aircraft wing, whatever aerodynamic model we consider is a incompressible, subsonic, transonic or supersonic, but we consider here incompressible. But for this gas turbine theory, where means aeroelastic analysis, we cannot consider incompressible aerodynamics. We have to consider compressible, because so many interference is there, and okay, compressible may give some result, but it may not be accurate enough. So, incompressible unsteady aerodynamic load, if you look at that, suppose this is a aerofoil section and it is vibrating in this mode and also in this mode. These two modes are combined. When it is vibrating, we cannot say it is vibrating only in this mode or only in this mode. When it is vibrating, both modes will be there. So, what will happen? So, let us say this is a aerofoil section, the flow is coming like this, and let us say it is oscillating like this, then there will be a vortex generated at the leading trailing edge. So, alter means it will have some vortex in a clockwise direction, few vortex, and then next time when it is going upward or downward, it will have opposite direction. Those vortexes are shaded in the downstream. So, the aerodynamic load whatever we calculate in the unsteady aerodynamic load will have two components. One is called instantaneous component, depending on what is the angle of attack, another is the history effect, means the flow which has already been passed from the through the aerofoil section, that is having also effect, that we call as the lag effect. That is why when we calculate the unsteady aerodynamic load, it is no longer a real number, it is a complex number. The meaning of the complex number is that there is a real number, means that is the instantaneous force. The imaginary part, that is the lag effect, because that will tell you if I convert into a time lag, I can convert that means the imaginary part with a time lag. I am sure you are aware of that when we do the this matrix complex number calculation, we will have let us say x plus I alpha I y, we get a angle and we get a amplitude. This is your amplitude, let us say this is x, this is y. Usually y axis we consider as a imaginary axis, x axis is the real axis, and this will give us the angle. Okay. That angle in physical sense is the angle, but when I am going in the time domain, it is a phase lag. The time difference between the force and the instantaneous force, means what I am saying, a vortex has crossed the aerofoil section, and that is having effect. Maybe delta t time before it has crossed that is having the effect on the instantaneous lift, that I am calling as the lag effect. That is why it will be a complex number. The unsteady aerodynamic load, because representation in complex number is relatively easier. That is why we use complex number. But if I can have a CFD code which can make the calculation in time domain, then there is no problem. I can take that also. But solving Navier-Stokes equation in time domain is not a so easy task. And when I am going in a time domain, every time step I have to solve a CFD code. It takes a lot of time. So, if I want to do with a full Navier-Stokes equation and time domain, do the flutter analysis, before that the aircraft can fly also. No, it takes a lot of time. Just CFD calculation sometimes takes a lot of time. And if you put on top of that unsteady aerodynamic load, unsteady CFD code, I am sure it will take 6 months or 1 year for a simple geometry, means a little bit complex geometry. Simple may be okay, but complex geometry it is not so easy task. That is why I am saying we may consider the complex representation of the system, so that we can make the calculation quickly. Because in the Nastran, whatever this MSc Nastran software, whatever code they have used 2 different codes. One is DLM, doublet lattice method, that is for subsonic aerodynamic calculation, and vortex lattice method in the supersonic aerodynamics. And whatever they have calculated, it may be applicable up to maximum 3 Mach number. You cannot go to high supersonic Mach number. Because there are limitations, and obviously you will not find any code available for transonic region. So, whatever we make the calculation, some extrapolation from the subsonic aerodynamic load or interpolation, same extrapolation from the supersonic to get, usually it varies, means transonic region it varies from 9 to 1.2 Mach number, 0.9 to 1.2 Mach number. In some aircraft maybe 0.95 to 1.2 Mach number. But usually there is no definite value, means established CFD code available to make the unsteady aerodynamic load in the transonic region. Let us proceed with this simple aerofoil section. So, the let us start with the first what I can say in the dynamic analysis, whatever lift load we have calculated and moment we have calculated, that I can just take as a time domain. That is the quasi steady, means just converting into the dynamic load. Quasi steady is slightly different. We are adding some part. You see, when it is oscillating in a steady aerodynamic load, what we have considered that aerodynamic control point is quarter chord point. But when it is oscillating like this, the control point has changed to 3/4 chord point towards the leading edge. So, there will be some due to this oscillation, there will be some additional lift force acting. Due to this, I will show you how it has been calculated. So, aerodynamic force acting on the wing is the lift, and it is placed on the quarter chord point for the aerodynamic center. At the aerodynamic center, there is also an aerodynamic moment acting around the flexural axis. The lift is defined positive downward. In this means there is a axis system definition. Lift is means here actually the downward deflection is the positive, and clockwise rotation is positive. This is the axis system, and then we have calculated the lift force here actually one important part, when the quarter chord point change to the 3/4 quarter chord means 3/4 chord point, the aerodynamic load or the due to this alpha dot, it will have a displacement. In addition to alpha, we will have additional alpha. Alpha will be coming, means additional angle of attack is coming due to the relative velocity of the aerofoil section, the h dot and also alpha dot, because at quarter chord point we will have h plus xf minus x alpha dot by u. This alpha dot by u, basically the velocity, if I plot this way, that will have additional that will have additional, means I can see that, let us say it was originally at this point, it has moved to this h and also it has rotated and it has gone to the quarter chord point. So, this total deflection will be h plus this displacement, that is alpha dot into xf minus x. Okay, that is the deflection, sorry, that is only displacement. So, it is not alpha dot, only alpha, I do not know, maybe only alpha. This is the displacement at that point. So, if I have a velocity in this direction u and deflection in means velocity in this direction due to this motion, that will be h dot plus alpha dot into xf minus x at quarter chord point. This will be inducing additional angle of attack. The additional means we had originally, let us say this is angle of attack, whatever we are getting here alpha. Okay. In addition to that, due to this hip velocity, there will be a relative angle of attack. This relative angle of attack is nothing but h dot plus alpha dot xf minus x divided by u. That is basically tan inverse. This is the additional angle is tan inverse of this. I can approximate, because this angle deformations are small in deformation, I can approximate as h dot by u plus alpha dot by u, this is the forward velocity, and xf minus x. Okay. This finally, the lift can be calculated from here. If I look at here, lift can be calculated from CL, means in addition to that whatever we have calculated earlier, in addition to that this CL will be 2 pi into A naught plus A1 into A1 by 2, that is the lift force, and the A naught can be expressed as alpha minus 1 by pi 0 to pi dz by dx d theta. Similarly, A n can be calculated 2 by pi. These I am not going into details of the unsteady aerodynamic calculation. If you open some unsteady aerodynamic load book, there you can get all these details how they have calculated, and then this relationship. So, now if I go to the next this that is what whatever I was telling, CL I will be calculating, means that is the mathematical relationship I am expressing in terms of simplistic equation, that is originally alpha t was there, h dot by u velocity due to hip velocity whatever change in angle of attack, then 3/4 chord point minus xf, the elastic means difference between the elastic axis, that is alpha dot by u. Now, this is the this 2 pi I have taken for thin aerofoil section, CL alpha is nothing but 2 pi. That is why I have taken replaced that CL alpha by 2 pi. So, this is the means unsteady means quasi steady aerodynamic load. If I want to make this as a unsteady aerodynamic load, this is as per the theory of Theodoson. What we have to do to make it unsteady load? This is a quasi steady aerodynamic load, whatever we have calculated here. If I multiply by Theodoson function, there is a function defined by Theodoson, which if I multiply by that function, it will become unsteady aerodynamic load. Otherwise, it is a quasi steady load. Then we can have one more terms. Okay, these are fine. Added mass. Apart from the circulatory lift and moment, the air exerts another force on the aerofoil, that is due to wing is forcing a mass of air around it to move. The air reacts and this force is known as the added mass effect. So, whatever I was telling earlier, if we look at that, see this has been added pi rho b square. Pi b square is the diameter, means half semi chord is the b, pi b square, that is the circular area, multiply by rho, that is the mass per unit length in the transverse direction, that is the mass. That mass is affecting some affecting this equation by a inertial force, though it is negligible, but it is having a significance. Then if I now put everything together, so lift force will be pi rho b square h double dot minus x f c by 2 into alpha double dot. Then we have pi rho pi b square u alpha dot, and then after substituting all these relations, basically means earlier equation we have not taken the this mass effect, and this is due to okay, this another mass we have considered here, no, this is inertial mass and this is the Coriolis force, inertial force due to Coriolis, means Coriolis force, basically that is one type of inertial force due to rotation. This is only due to heave motion, effective heave motion, but it is having effective rotational motion also rotational acceleration. that is the Coriolis force, and this what we are getting here is nothing but the usual unsteady means quasi steady load. Same thing we have converted to moment also. So, now this equilibrium equation, if I look at here, you will be getting the mass matrix into displacement means acceleration, displacement double dot is time second derivative of time with respect to time, and stiffness matrix into displacement. Right hand side is the lift force and the moment force. In addition to lift force and moment force, we have added two forces, Pt, that is the means due to gust load, Rt, this is the rotational moment due to gust load, the additional force. It may be gust load or it may be inducing some instantaneous load when something is fired from the aircraft. Let us say for a fighter aircraft, usually for transport aircraft that type of force may not come, but in the fighter aircraft when missile is fired or bomb is dropped, there will be a reaction force acting on that we can define as a Pt. See here, if we look at this lift force and moment force, aerodynamic lift and aerodynamic moment, those are not independent force. Those are not independent force, they are dependent on the deflection or rotation of the wing or the aerofoil section. That is why if I rearrange, let us say Pt and Rt I am not considering, if I rearrange them, I can take it to left side. So, this equation becomes a something into right hand side equal to 0. That is the equation what we call as the that is why we call this system of equation as a self excited system. Self excited system means the aerodynamic load is developed which is not independent load. It is the function of deformation, it is the function of bending deformation, it is the function of rotational deformation, and that is inducing the lift force and moments. If I take appropriately to the left hand side, the equations, because we have some terms H double dot, alpha dot, we have then only alpha, only H also there. So, all these if we take in the left side, we will have right side equal to 0, and I can take the acceleration part is nothing but equivalent aerodynamic moment, aerodynamic mass, H dot related or alpha dot related equivalent damping force, aerodynamic damping, and the forces, aerodynamic forces which is related to alpha or only H, those are only for only H there is no lift force, either alpha or H dot, alpha dot, H dot, H double dot, alpha double dot. So, we can rearrange them and take it to left side and get a equation right hand side equal to 0. So, here three possibilities are there, means if I increase the velocity, mass may, effective mass may become 0, or effective damping becomes 0, or effective stiffness becomes 0. Usually effective mass becomes 0 is not a feasible solution, because it does not happen, because aircraft mass of a aircraft or any means aerospace vehicle is very high compared to the mass of the air. So, that possibility may not be, even you increase the velocity as much as possible, it may not come to that situation. But other two possibilities are there. There is a possibility when damping becomes 0, effective damping becomes 0, that we call as a flutter. When effective stiffness becomes 0, it becomes divergence. So, in the dynamic equation, whatever equation I am getting, if I do the means flutter analysis for a very high velocity, for a means velocity beyond certain speed, I can get a situation when divergence I can identify also. The mode which is related to 0 frequency gone to 0, it will be going to 0, and at that point damping also will become 0. That is the divergence speed. When damping becomes 0, but frequency does not reach the 0 position, frequency is having non-zero values, that we will call as the flutter point. Usually flutter happens before divergence, that is why flutter is more important than divergence. Divergence usually means may not be feasible in the range of the velocity whatever aircraft can fly. So, in the aeroelasticity, what I am saying, we can say that A plus rho b square into B q double dot, A is the structural mass, rho b square, rho pi b square into B, that is the aerodynamic mass, C I am taking here, let us say structural damping, plus rho u C into pi d into q dot. This part is the aerodynamic damping and this part is the structural damping, and E is the aerodynamic structural stiffness, pi u square C pi f into q, that is the aerodynamic stiffness, that is equal to 0. We can have this situation what we call as the, when right hand side equal to 0, the equation what we call as the stability equation. This is not a, because we cannot get a definite solution of u dot u double dot, those are all relative displacements, velocity, acceleration. That is why means in that case we are calling as the stability equation. the similar situation of buckling or similar situation of normal mode analysis, vibrational analysis, where right hand side equal to 0. But if right hand side equal to non-zero, then we can get a definite value of displacement. Let us proceed. So, finally, if I take all these values, rearrange them, I can get this is the structural mass, this I am taking a aerodynamic mass, this is entirely aerodynamic damping, structural stiffness and structural aerodynamic stiffness. These are the values we are getting it here. So, in a matrix form I can write that M mass matrix into d double dot. I am just defining that d as a vector, displacement vector. C is the damping matrix, d double dot. K is the stiffness matrix, d double d into d, sorry, C into d dot, and K into d. Right hand side is the aerodynamic force. Aerodynamic force can be function of displacement, velocity, acceleration. Similarly, I can rearrange them to get the equation in a, if there is a external other than this self induced force, we can have a force, because gust is a gust, whichever force it is means applying on the structure, it is not depend on the displacement, it depends on the gust velocity, basically the upward velocity or the forward velocity. We can have gust, two type of gust, one is the horizontal gust or we can have a vertical gust. Usually horizontal gust is not that important, means critical, vertical gust is the critical, means there is a possibility of means happening this vertical gust, because in a particular region due to pressure difference there may be, or heat difference, means thermal difference, thermal layer difference, there may be a air column moving upward or coming downward. So, if we have a this air column coming upward, it will be upward this gust load, downward gust load. Probably you have heard in some means transport aircraft, maybe suddenly they got a down, means almost 1 kilometer down of the aircraft due to sudden gust. But under that condition, means it is designed in such a way that maybe in under that condition structure is not unsafe, structure can be safe, but it can lose the height or it gain the height, it can gain height, because suddenly it will push upward. That type of situation may happen. Typically in the transport aircraft, people feel that suddenly in the night when they are flying in a particular region of means when we are going from India to the US, somewhere in the this desert area, maybe they are crossing in the desert area, there it may happen, because air column may be there either upward or downward. The aircraft may suddenly feel either the passenger will feel that they are dropping or they may feel that they are going up, but still it is safe. That's because it has been designed with the taking care of all the loads. Let us look at that. Usually whatever I have shown here, it is based on the structural deformation, means physical deformation, but aeroelastic analysis, dynamic aeroelastic analysis specifically we will have to do in the modal domain, where first modal analysis is done, then we will be getting modal vector phi. With respect to phi, we will be non-dimensionalizing, and then we will get the all aerodynamic loads, means this m bar is the modal mass, c bar is the modal damping, k bar is the modal stiffness, and then right hand side will be modal aerodynamic load, which is function of q, q dot, q double dot. Now, let us see how we can solve these equations. There are several methods of solution of these equations. One is called K method of Flutter solution, or sometimes we call as the Theodorsson method of Flutter solution. Theodorsson is the first person who made all these calculations, and that is why we means the method is given in that name, in his name. In the textbook you will find though it is calling as the K method, but it is a in the textbook they have defined as a Theodoson method. Here they what they do basically, the aerodynamic load whatever is acting they consider as equivalent aerodynamic mass. Instead of taking it to stiffness and damping, they are taking equivalent mass. Then when you are means getting the matrix equation, you will be determinant of the matrix, because right hand side equal to 0 means matrix into displacement will be equal to 0. Your displacement cannot be 0, no. If you take displacement equal to 0, then there is no solution available. Only possibility is that the determinant of the matrix is equal to 0. So, if I take determinant of the matrix equal to 0, it is a complex matrix, no. In the Theodoson method, what they do basically, original Theodoson method, what they do, the equation they divide into two parts. One is the real equation, another is the imaginary equation. Then for different forward velocity, they find the roots of the real equation and the imaginary equation. There is a point where they these two real roots and the imaginary root coalesce, that we call as the Flutter point. But K method problem is that we cannot physically explain what is the flutter, what is flutter, means because we are dividing into two equations, a real equation, another is imaginary equation. Imaginary I am taking it out, taking it out, only the real part of the imaginary equation, and then solving separately to find out the roots and then going ahead. Then there are some modified K method also, that we call as the KE method. Then another important method is called PK method. PK method means P is nothing but the complex eigenvalue, K is the reduced frequency, means you are finding complex eigenvalues for different values of reduced frequency, what we call as the, in aerodynamics term they call as a Strohal number. That same means non-dimensionalized frequency parameter, that we call as the K, PK, means solving P for different values of K, where basically you are taking with respect to the forward velocity. In this PK method, the real part the aerodynamic load related to damp means velocity is considered as equivalent aerodynamic load, and the other terms everything put together they are taking into aerodynamic, means this is basically I can say that right hand side whatever from the aerodynamic unsteady aerodynamic computation, though I have explained those mass matrix, stiffness matrix, all these, but finally if we go to the right hand side equation, it will be basically having two parts, real part and imaginary part, because double dot I can substitute as a harmonic equation and then it becomes a stiffness value. So, what they are in the PK method, what they are taking, the imaginary part they are taking equivalent damping, real part taking equivalent stiffness. So, if you look at here the equations I have 1/4 rho C V QHH I, that is the imaginary part. QHH what I am calling as the aerodynamic influence coefficient in a modal domain, QHH I, and here I am getting QHH R. Then I am solving for a complex eigenvalue analysis. In this I will be means basically converting this equation. I am sure some of you are aware of the state space method. Have you heard about state space method? No. Whoever has done control or control theory or the vibration control, structural dynamics, vibration control, they are a little bit familiar with the state space method. State space method means usually we will have mx double dot plus kx cx dot plus kx equal to 0. What do we do here? Basically we are taking displacement as a state. When we are expressing this second order equation to a first order equation, I will be taking x and x dot are the two states, displacement and velocity are the two states, then I can express this equation in a first order equation. A x dot plus k u that way equal to 0, and that advantage in that we have to deal with the first order equation, and most of the solver in the MATLAB also you will find that there are solvers available for first order equation. So, that equation we are calling as the state space equation. So, once you means convert this equation, whatever we are getting in the PK method, I will be converting into state space method. I am taking here u h is the displacement, u h and u h dot, these two are the states, and then expressing in a single means first order equation, first order time derivative equation. Then I am finding the complex eigenvalue of this equation, that is A minus rho I, sorry P I. P is the complex eigenvalue, I is the identity matrix. Once I solve these equations, I will be getting the roots, complex roots. The real part will dictate how much damping is available in a particular mode, and imaginary part will say what is the frequency. Here actually the solution is done in a mode tracking wise. You will be taking starting let us say the iteration from 50 meter per second as the velocity. For that velocity and considering mode 1, what is the k value, because B is known, B is the semi chord, omega B by u, okay, you will get a k value. So, a priori you will be calculating that complex means unsteady aerodynamic load in the k domain. For different set of discrete values of k, you will be calculating. Then when you are getting doing the solution, this Flutter solution, you will be getting, let us say mode 1 you are tracking, you got k value. For that k value you do not have aerodynamic load. So, you will do the interpolation or extrapolation, then solve the eigenvalue. In that eigenvalue again you find out what is the frequency, what is the damping, and check what is the value of k. That k iteration has to be done to converge it. Then only once it is converged, then you go to next velocity. Like that you will be tracking for each mode. Each mode once you have done it, then you can plot frequency versus means forward velocity versus damping versus forward velocity, frequency versus forward velocity. When damping becomes 0, you say that is the Flutter point. That is the, that is why PK method is means you can means everybody uses PK method, because you can physically explain what is the meaning of Flutter. The Flutter point is the point or velocity when the overall damping in the system becomes 0, that we are calling as the Flutter point. Now, if I take the response at that point, I will be finding that it is harmonic oscillation. I will just show you, I have taken here a 3 degrees of freedom model, taking 2 springs k h and k alpha, in addition to that a control surface deflection k beta. K beta is the stiffness of the actuator, and then we have calculated how it is responding, means for different velocity of the forward velocity of the vehicle, how these frequencies are changing. We can represent in a different mode. One I have discussed about the damping versus damping versus forward velocity, frequency versus forward velocity, or I can take as this root locus plot. In a complex domain, when I am getting a root, I can take a real part is the x axis, imaginary part is the y axis. Then I can track the modes. If you look at that, this is the bending mode and this is the torsional mode, and this is control surface mode. Usually control surface mode will be higher frequency. So, if you look at that, for a velocity when it is starting, the damping is increasing in this direction, means for higher velocity it is going in this direction. Bending mode will not flutter, whereas in the torsion mode it is initially it was increasing, then it is coming down, suddenly it come down and cross from left side to right side. In a complex domain, when I say that imaginary part crosses from left side to right side, whenever it is in which point or which velocity it crosses, that is the flutter velocity. So, this is another way of representing the flutter point, that is the root locus plot, means how root is varying for different forward velocity. Now, if I take the response for means suppose I take the response just below the flutter point, I will get a response like this. The response will be dying down, okay, or stabilizing to some velocity, means some amplitude. Similarly, for the other one. But if I take the response, means response, how I am taking the response? I have the system matrix. Now, I am giving who are habituated to do the control analysis. We get a means state space method. When you are expressing in the state space method, I can get a step response of the A matrix, state response of the A matrix. When I am taking a state response of the A matrix at a velocity lower than the flutter velocity, I will be getting a response like this. If I am taking response at the flutter point, I will say I will get a harmonic oscillation, means there is no damping, whatever it is means unit force I am giving, whatever response it is coming, it is oscillating in that point, in that way. Then we have another point, means we can take the velocity higher than the flutter velocity. What will happen? It will over the time, this is the time response, over the time the amplitude of oscillation will grow. That is the means response, or the physically it happens. Actually, the time domain response is the physical response. All whatever we are doing in between complex, just to represent in a that same thing, time domain equation information in that complex domain. And let us show you, I will show you this simplistic equivalent aircraft model, where fuselage is taken as a planar form, wing is taken as a planar form, and there is a fin, control surface, vertical fin, that is having also movable part, control surface, and the wing also will have movable part. If I have this type of means simple configuration, I can do the maneuvering condition, maneuvering simulation. Without that, without control surface, I cannot do any maneuvering means simulation. But with this means with fixed wing, without control surface, I can do the flutter analysis. If I just see the flutter analysis of this particular model, see there is a bending mode, there is a torsion mode. This is lower mode, usually bending mode will be lower frequency, torsional frequency will be little higher. And if I take the damping, you will be finding that damping of the torsional mode crossing 0, and similarly the frequency of the torsional mode will be coming down, bending mode will come up. In this case, it has not coincides, but in a typical situation, in a simplistic model, it may coincide. Now, let me see whether it can, I can show you the video. Means at the flutter point, we cannot really identify whether it is vibrating in a more bending mode or the torsional mode. It is a combination of deformation. That's what I am showing it here. For a different forward velocity, it is vibrating like this. Initially, it was torsional deformation, slowly it is going to bending deformation. If you see, look at here in the vibrational mode, torsional mode to going to means bending mode. Means exactly at the flutter point, we cannot distinguish between which mode it is fluttering, whether it is a torsional mode or it is a bending mode. It is a combination of torsion mode and the bending mode. So, I think I will stop it here. So, if you have any questions.